Hello and welcome to episode 9 of Super Simple Scala. Today we will talk about monads. First, we will define what exactly is a monad. A monad is just something that defines a flatmap, where flatmap is just something that takes in whatever's inside the monad and returns the thing that sort of contains it, I guess, if that makes any sense. We'll also have to define a related concept called functor. A functor is just something that has map. If it has map, it's a functor. Not sure if this is... yeah. Anyway, so we've got this concept of monad, and we've got this concept of functor. The simplest kind of monad is the identity monad. All that it does is it contains something, and whatever sort of closures you pass into it, it applies those closures as if you were calling them directly. So let's look at this. We've got identity monad, wraps up an integer, and it extends int functor, so it's going to have map, and it extends int monad, so it's going to have flat map. So you've got overriding this and overriding the other thing. All right, what is map? You pass in a function that takes in whatever type is on the inside, and it returns whatever type is on the outside. And it applies this function to whatever is inside the monad, and you wrap it back up in a monad again using the constructor, and you end up returning something that is of the monad type. What is flatmap? You pass in a function that takes in the type that is contained. It returns the monad type, and so you just can call it directly, and the type that comes out is going to be the monad type. Really, really, really simple. So how do we use it? Let's say we do identity monad of 1. All that it does, we have just an identity monad that wraps up the number 1. Then let's say we map and we pass in a function that does +1. What happens here? You can actually, if you want to, you can set a breakpoint and actually step into it. But basically what's going to happen is at this breakpoint, if you step into, what's going to end up happening here is you're going to pass in this function, this +1, which is going to be your f, and it's going to apply f to I, which is 1. You're going to get 2 in here, and that 2 is going to be wrapped up in the int monad, the identity monad again. So when we get out of it, we're going to end up with something whose value is identity monad 2, as you can see right there. What about flatmap? Really simple. We pass in a function, takes in, let's call this variable int. You do, let's say you're going to do, it's going to return, instead of returning an int, it's going to return an identity monad. So it's going to return int +1 identity monad. And all that it does is it takes this, step into, takes this whole thing, assigns it to f, applies it to I, you get out, step in, you're going to get out identity monad whose value is 3. That's it! That is it! You know you just learned what a monad is. It's that simple. Now let's learn some syntactic sugar that makes it, well, let's make it a little bit fancier. So what's going on here? We've got IntMonad3, flatmap. We have something that takes in the 3 from the IntMonad3 and then wraps it in identity monad, 3 plus 1, and then maps it to 3 plus whatever goes in there, where whatever goes in there is going to correspond to identity monad of 3 plus 1. Now what happens in this statement? Let's step into it too. Step into. Well, if we go to the desugared code, so let's go to this conveniently located desugared code and look at what this compiles into. Let's just hide this for a second. We've got int monad7 equals this big ugly mess. Let's separate this out just so we can focus on it separately. All right. Let's get rid of main.this. Get rid of some. We don't need apply. You can just call this x2. $sign is for synthetic variables. All right. So what is going on here? So int monad3, flatmap, and then this whole thing. So what's the first step? The first step is this big whole thing takes in 3 of type int, returns all of this stuff, is going to get passed into this flatmap. And what's going to end up happening is that big function is going to get applied to I, where I in this case is 3. So we take in 3, and we go, all right, let's put in 3 in here, and what are we going to get out? We're going to get identity monad of 3 plus 1. This is just the same as that. We're going to get identity monad of 3 plus 1, which is going to end up being identity monad of 4, mapped to something. All right, now we repeat the step again. So we take this function in, let's see, let's make it, let's say we're doing, so we're taking this function in here. So now we have identity monad of 4, and then we're mapping it to this function. So we're taking this function and we're passing it into here. So we're going to have, in this case, I is going to be 4. That's what's in our identity monad right now. So I is 4, and we're going to say, we're going to apply this function to I, which is going to be, so x2, we can call this, this x2 is going to be 4. So we pass in 4, so we're like, okay, 4, 3, so we've got this 3. So because of the way closures work in Scala, and so closures are like nested functions. I mean, they don't have to be nested, but they have access to their outer scope. So in this case, this function here, this x2 of int 3 plus x2, this function on the inside has access to this, the memory, the value of this 3 on the outside. So the inner function has access to the parameter of the outer function. So we've got 4, a function that takes in 4 and returns 3 plus 4, where this 3 comes from the original int monad 3. So what's 3 plus 4? 7. So we end up with int monad 7. So all that we did was we just took 3, we added 1 to it, and then we added the original 3 from the beginning to make 7. Now, why did we go through this convoluted roundabout way of adding 3 plus 1 plus 3 to make 7? Just to understand the concept. In the real world, obviously, we're not going to be using monads to add 3 plus 1 plus 3. Now, for this little bit of syntactic sugar over here, we're going to make it a little bit prettier. We're going to have int monad 7, we're going to redo it, but this time we're going to use this concept of a for yield, where what a for yield does is it's actually going to, if we look at the desugared code, let's isolate this out for a second. What's going to actually end up happening that looks good. All right, so it's actually going to end up turning into flatmap, and then actually I can leave that. It's going to end up turning into flatmap, and then map, and then 3 plus 4. So if you actually looked at sort of this, where we have int monad 3 flatmap, and then sort of identity monad plus 3 map, and then 3 plus whatever, these are pretty much the same thing, right? So this here is just the syntactic sugar, but what makes the syntactic sugar really nice is the fact that if you looked at this original sort of how it was originally, we had the 3 from int monad 3, and we got access to sort of the memory from the value of 3, and then we used it. We had took the 3 from the outer scope, the outer closure, and we used it in the inner scope. It's almost as if that 3 was like a variable or something that we had access to. And by writing it like this, int monad 3 corresponds to 3, we're making it very visible that this 3 was something that was extracted from int monad 3 and that is sort of available to access at a future point in time. In this case, within the inner closure. So in this case, what we end up with is if we look over here, we have int monad 3, and then we have flat map to 3. So we have flat map to 3. So we're saying that this 3, we have access to the memory of parameter whose value is 3. And then we're saying identity monad of 3 plus 1, map. Well, before we do the identity monad 3 plus 1, we want to say that, this 3 plus 1 is, we want to say like we can extract this 3 plus 1, I guess, into something, let's call it 4. Here we're using an underscore, but if we wanted to, we could say something like 4 if we wanted to be a little bit more explicit and not use the underscore. We could say that this 4 corresponds to the parameter for that, the same way that this 3 corresponds to the parameter for this. So this is the sort of memory that you can access from the outer scope, and this is sort of like the value that is accessible by the inner scope, and the very last computation that we do is going to be 3, which is from the outer scope, plus 4, which is from the inner scope, and it yields 7. All right. Super simple, right? If you don't understand this, you're not going to understand any of the more complicated monad stuff. But if you do understand this, if you can write this code, if you can step through it with a debugger, you're good. I mean, you're ready. You're ready for the real deal. One of the most common places where people sort of first become immersed in monads is in a programming language called Haskell. And the reason for this is because in Haskell, if you want to do Haskell print IO or something, the thing about Haskell is if you want to do something really, really, really simple, like just print something out, you end up using this sort of do notation, which is actually kind of similar to the Scala for yield that we just saw. And we actually end up, instead of using side effects, we end up using a monad that sort of accumulates the IO in a sense. And this monad is one of the first monads that you will encounter if you learn this language that Scala is influenced by. And the name of this monad is called the Haskell print state monad. You'll see you'll see the way it works is, the way IO works is, let's see. I'm trying to find it, but you can think of it almost as something that sort of takes in a terminal and then sort of produces the value that you want plus like a new terminal, rather than sort of modifying. It sort of accumulates the changes in place. The way we're going to represent that is with the state monad, which is what we're going to learn next. This looks kind of confusing, but all what this is so we've got monad, we've got flatmap. What I did here is I defined a type called state monad t, where all this is it's a type that extends monad. It either is a subtype or it's the same type. And instead of taking in t and returning monad the way we did with the identity monad, where we took in t and returned identity monad, instead we are returning the I'm lost in my own code. Give me a second. Instead we're returning state monad, which is just a subtype of monad. And what this allows us to do is it just allows us to override. So you see this override def flatmap. Don't worry too much about it. If you kind of saw the episode on the type system, this is just sort of a way of making the types as sort of specific as possible, instead of just using the sort of super type for your return types. But anyway, so you've got this flat map, which we override in the subtype because this extends monad. We've got this really weird thing called run that takes in a state and returns a result in a new state. And then we've got map, which you pass in a function that does some sort of transformation from result 1 to result 2. And we've got flatmap, which does some sort of a transformation from result to state monad of result 2. That sort of augment this sort of transformational process. How does this state monad work? let's define incrementing state monad. Let's see if I can actually make this font bigger. Give me a second. Font, increase font, let's see, increase font size. Sorry. Let me make it size 26. There we go. All right, so incrementing state monad. All this does is it just increments numbers. So we pass in a function that takes in a state of type int, and all that it does is it increments the state to make a new state, which is just the old state plus 1, and it gives us a value that is the original state as a floating point number. What is the point of this? Let's say we have 1, and we did incrementing state monad run 1. We're going to end up with 2, which is just 1 plus 1 is 2, and then 2 as a floating point number. So we've got this floating point number and this int. This is just 2.0, this is just 2. We do it again, incrementing state monad run 2, we're going to get 3, floating point 3. Actually, give me a second. This is going to be the original state. So this is actually going to be 1 float, 2 float, 3 float. My bad. Yeah, so if we run this, if we pass in 1, we're going to get, state plus 1 is going to be 2, and then 1, 2 float is going to be 1 float. Okay, so why do we care? Let's say you have a random number generator. With a normal random number generator, if we had something like val r equals new rand, and let's import alt enter new random, Java util random. All right, let's say that we had this random number generator and we did r dot sort of next int, and we did this a few times. What's up? All right. And let's create a few variables. Let's call them r1, r2, and r3. All right. So let's say we had r1, r2, and r3. So every time this method is executed, it has a side effect. So if you were to execute it multiple times with the same input, you're going to get a different output every time. You're going to get a different random number because every time you execute this, some sort of global something is being modified. So this is an impure function, and we make it clear that it's impure with these by leaving in the curly braces. If we left out the curly braces, we would be lying. We would be saying that this is pure when it's really not. So this is an impure function. Now, why is an impure function bad in this case? Well, let's say that you wanted to go backwards in time. You wanted to be able to go, all right, here's a random, and then here's a random, and then here's a random, and then, oh, let's go back to the previous random, or let's go back to the original random. Let's say for testing purposes, you wanted to sort of be able to replicate the results, get the same results every time you test it, and be able to replicate it so you can check to make sure or figure out what's wrong. So if your random number works like this, you can't go backwards in time. You can't sort of, if it were like a pure function, if you were sort of, I guess, say you were just saving everything in place, you would be able to sort of go back. You would be able to kind of go forward and then sort of, undo, right? This, there's no undo. You can't go back. You can't undo it. You can't go backwards. Every time you call it, you go forward and then, oops, sorry, I can't replicate it. I'm sorry. Some weird bug happened and I'm stuck. All right. But if you use pure functions, if this was a state monad, instead of this next int sort of modifying a global variable and not being able to access sort of the original generator, what it would do instead is it would be a monad. And this isn't the actual monad part. Run isn't a monad method. The monad method is actually going to be, a flatmap, which we'll see later. But in this case, what makes the state the concept of in this case the sort of immutable pure way of doing this is that if you pass in 1, you're always going to get, let's say if you pass in, our seed is going to be 1, we're always going to get 2 and sort of 1 float. But if this were a random number generator, we would pass in a seed. So this would be let's rename this into refactor, rename seed. This would be the seed for our random number generator. Let's call this actually seed 1. And then we would output, instead of integer 1, we would output seed, integer 2, we would be outputting seed 2. Instead of 1 float, we would have something like rand 1. And then instead of 2 float, we would have rand 2. And then this 3 would be refactor, rename seed 3. This would be seed 4. And this would be refactor, rename rand 3. So if this were, instead of being just something that increments integers, if it were a random number generator, so let's rename this, let's call it random, right? So now we're representing it with the the pure version, where if we put in the same input, we get the same output. So in this case, we take this random, we pass in a seed, the original seed, we get out the next seed and the first random number. We take the next seed, we pass it in again, we get the third seed and the next random number. What if we want to go back in time? What if we want to sort of replicate this? Well, it would be really easy to replicate, because all that you would have to do is just copy and paste, and all that you would have to do is just copy and paste, and let me put a little semicolon. The way that these scopes work is actually this whole thing is going to return the last thing inside of the curly braces, which is actually going to be the result of equality, which will be unit, but don't worry about that. Anyway, the point is that now we have sort of this, we've got, we can call it twice with the same seed, and we're going to get out the same random number. So we can just go back in time and say, hey, we got this weird random number. It doesn't look like it's really random. Can we replicate the results? Sure. We just keep all the seeds in a big list, and so we can replicate any of the random numbers that we generated by passing them in again, just because we keep the seeds like saved up. This is kind of how I/O works in Haskell. So you can kind of think of it as instead of passing in a seed and getting out a new seed, you're kind of like passing in the world, the environment or something like that. You're passing in the old environment and you're getting a new environment. Haskell is weird. But yeah. Now if we look at map, let's say we passed in something that takes in a float and returns that float as a double. what this map is going to do is it's going to take this float to double, and if we go to map, so if we press Control B to jump to declaration, it's going to do the original call to run, which is just going to increment int +1 and then int to float. So we're going to have the original integer converted into a float and then the original integer +1. So we're going to do the same as if we were doing the run. And then after we do the run, we're going to do the function that we passed in, the float to double function. And then we're going to get this, instead of getting int to float, we're going to end up with int to float dot to double, and this new int, which is just int +1. So what's the point? Well, the sort of function that is transforming your result data is, give me a second to get my charger. The function that is sort of transforming your, let's pretend it's the function that is generating your random, the function that generates a random number from your seed, or the function that generates something out of your current integer or whatever. That function is having another function sort of added on top of it. So you can sort of say, all right, in the state monad, we're first going to do this, and then we're going to do this, and then we're going to do this. And every time we map and flatmap, we're adding another sort of chain to the series of steps that we're going to do when producing something from a seed. So let's go back to where we were originally. So now when we call run, in addition, instead of doing outputting a float, we're going to output a Control Q double. Because after calling the original method to float, we're going to be calling this on that. Flatmap, here we're doing something kind of similar. We are, instead of returning, instead of just returning, float.toDouble, we're returning a monad that wraps up whatever is on the inside. So flatmap is kind of like map, but the return type has the monad instead of just being sort of the raw thing inside of it. So in this case, it returns a monad that we're leaving the int the same. So the int, this state monad that we're adding to it doesn't change the int, and it converts the float to double. And if we look at sort of Control B flatmap, we'll see that we're going to call run. So int to float and then int +1. So that's the same as it was in map. And then we're going to sort of call this f function, the thing that does the float to double, and this is going to cause the float to become a double, and it's not going to change our current count. But what it is going to do is it's going to change this into float into it's going to change this into float into float to float dot to double. So it's going to sort of add an extra layer to it, and then call run with new int, which is just going to be sort of the next thing in the chain, and there we go. You'll notice these little dot trace standard outs. If you were to sort of run this without the debugger, you would actually get these nice clickable stack traces, 2, 3, 4. This is provided by an implicit conversion. If you press Alt-Enter, we can Alt-Enter. That is normally if you press Alt-Enter, you should be able to make implicit conversions explicit. But it is not doing that right now, and I don't know why. One sec. Real quick. Temp. Provide, there it is, and provide implicit conversion. And what this does is it sort of adds this nice little wrappable, implicitly traceable temp.trace standard out. And what this does, Control B, is it's an implicit conversion. So what this is going to do is, sorry about the lighting. What this is going to do is it's going to take in something and return implicitly traceable of that something, where implicit trace is going to provide these nice methods to print things to your terminal with these nice clickable stack traces that you can navigate up and down with Control Alt up and Control Alt. You can kind of jump around your Control Alt up. Yeah, you can jump around your sort of code base in sort of chronological order of all your print statements, which is really convenient if you want to skim. But yeah, just import that. That's a feature that kind of came from the library that I wrote. Scala.trace, the library's name, yeah. So yeah, anyway, the point is that basically all that you needed to learn from this was that what a monad is. So in this case, a monad is just something that has the flat map, that sort of has this shape where it takes in something and returns a monad. You learn what a functor is, where it takes in something and returns something. If you want to learn more, there is a very nice book written by a guy who knows a lot more than I do. Programming in Scala 2nd edition. No, that wasn't the one I was thinking of. Was Functional Programming in Scala. Yeah. So this red book, this guy knows all the functional programming stuff. So get your monad stuff there. And if you're curious about like for yield notation or stuff like that, there's a lot more detail in the Programming in Scala 3rd edition, which you will find. This is 2nd edition, but if you were to look for 3rd edition, it's there. And if you're cheap, I think that there's a way to get this the 2nd edition as a PDF. I think so. It might be not here. Maybe wherever. Anyway, so you learned for yield notation. Oh, there it is. You learn for yield notation, you learn map, flat map, you learn identity monad, you learn state monad. Go learn functional programming. Bye.